Okay, we are live. So hello everyone and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I'll be your host today. This is webinar number 160, and we're having Josu Hernandez Garcia as a speaker. Josu carried out his PhD at the Institute for Theoretical Physics of the Autonomous University of Madrid in Spain, which was followed by a postdoc at seesaw in Trieste, Italy. Then he had a second postdoc at the University of Budapest in Hungary, and is now a senior postdoc at IFIC in Valencia, Spain. Today, Josu will give us a talk about current limits on heavy neutrino mixing with an emphasis on effective field theory, and we're very happy to have him as a speaker today. Before we begin, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system. And these questions, as always, will be passed on to Josu at the end of the talk. So we're all yours, Josu. Please go ahead.
Thank you. Let me share my screen. I think you should see something already. Put it on. Do you see?
Yeah, perfect.
Hear me well? Okay,
all good.
Perfect. So thank you for the introduction and thank you for the invitation to the webinars. Today I want to talk about the heavy neutral lepton mixing and the connection with the neutrino standard model effective field theory. So first of all, a little bit of introduction on the standard model and the open problems. So we all know that the standard model is a successful theory. It predicts a wide variety of phenomena. It has been tested in a huge number of experiments with incredible accuracy. That is perfect. However, we still have some open problems. I prefer to call them open opportunities because they represent our best window to prove for new physics. So among all the standard model open opportunities or problems, I picked the neutrino oscillation to be the most interesting one. It comes from the discovery of neutrino oscillations that points out that neutrinos have non-degenerate masses and that the lepton flavor is violated. And from my point of view, it's the most interesting one because it could give us a hint or a key to understand some other open problems of the standard model. For instance, in some models, the neutrinos provide a dark matter candidate, or they could help understanding the flavor puzzle that deals with the lack of explanation in the standard model for the dissimilar Yukawa ordering, or the different patterns in the quark and lepton mixing matrices. And finally, also some models of heavy neutrinos provide necessary ingredients to produce baryogenesis through leptogenesis, and in this way explain the matter-antimatter asymmetry of the universe. So I will assume from now that the neutrinos are massive, and if this is happening, then it will be a misalignment between the two bases, okay? The physical basis of the massive neutrinos and the flavor basis of the interaction neutrinos. These interaction neutrinos, electron, muon, or tau, will be a combination, a linear combination of the massive neutrinos nu1, nu2, nu3, where the combination is given by the elements of the mixing matrix, this PMNS matrix that appears here in the charge carrying interactions. Okay, so we'll measure this through weak interactions. The PMNS matrix is a 3x3 unitary matrix, and it can be described by three angles that are called the solar angle, the atmospheric angle, and the reactor angle, and one CP violating phase, delta. In the case of Majorana neutrinos, we will have two additional phases, the alpha 1 and alpha 2, that will not participate on oscillations. This term cancels out. So what is called neutrino oscillation parameters are the subset of parameters that are appear in neutrino oscillation experiments. These are the three angles of the PMNS matrix, the delta CP phase, and the two mass splittings of the neutrinos, okay? In neutrino oscillations, we don't measure neutrino masses, we measure the difference of masses, actually the difference of masses squared. So these are the six neutrino oscillation parameters, and this is the leading and subleading dependence of the possible neutrino oscillation experiments that we can build, which are solar, atmospheric, or accelerator-based neutrino oscillations. experiments. So as you can see, there is a leading contribution to different of these neutrino oscillation parameters and also a subleading dependence, which is mixing all of them, and with this making the measurement of these neutrino oscillation parameters more complicated. So in the present status is that we don't have a present value for these parameters. We have an overall view that is coming from a global feed to these neutrino oscillation experiments, like this global feed performed by the nu-SMEFT collaboration. So these are the allowed regions for these oscillation parameters. And the best fit values correspond to this table, where we can see that we can have some good values for the atmospheric mixing angles, but we have still some unknown values. For instance, the delta CP phase, we start to have now some hints on the value from present measurements, but the error bars are still large. So we still don't know if the CP violation will be maximal in the neutrino sector or not. Also, the octane of the θ23 is still not clear. You can see here a degeneracy on the octane of the θ23 angle. Or finally, the sign of the atmospheric mass splitting is not determined yet. This sign is important because it gives rise to the two possible orderings of the neutrino. The normal ordering is the one in which the lightest neutrino is the nu1, and it has the biggest amount of nu-e. The inverted hierarchy is the one with the lightest neutrino to be the nu3, with the lightest amount of nu-e. On top of this, it will be also the overall masses of the neutrinos that we don't know from neutrino oscillations. Okay, so this scale from whatever value to the nu1 and nu3 is unknown. It is still compatible from neutrino oscillations to have two masses neutrinos, the nu1 or the nu3. So this absolute mass scale can be measured or determined in different experiments. The present bounds are coming from single beta decay. For instance, the Catherine collaboration is setting a bound on 0.8 electron volts on the effective, on this combination, that is called the effective masses of the electroneutrino, or from CMB measurements from the Planck collaboration that is saying that the sum of the lightest pieces has to be below 12 electron volts. So, okay, we have neutrino oscillations that are pointing neutrino masses, and let's try to explain them in the standard model. So in the standard model, all the fermions are getting the masses through the Yukawa interactions, where the Higgs is mixing the left-handed and right-handed components, and after electroweak symmetry breaking, they generate what is called Dirac mass for the fermions. So this, we can try to replicate this for the neutrinos and build a Dirac mass for the neutrinos, but we realized that we cannot do it because the right-handed neutrino is not present in the standard model particle content. Alternatively, since the neutrinos are neutral fermions, the only neutral fermions, we can build a new kind of mass term, which is a Majorana mass term for the left-handed neutrinos. However, this term is violating the SU2 cross U1 symmetry, which actually is broken by the Higgs mechanism. And in fact, this kind of term, the Majorana mass term, can be generated through the Weinberg operator after electroweak symmetry breaking. Okay, so this is the Weinberg operator after electroweak symmetry breaking will generate a mass term for the left-handed neutrinos, where the Majorana masses is given by the coefficient of the dimension 5 operator. However, this is a dimension 5 operator, again, is not included in the standard model because it's dimension 4 of theory, and it means that in the standard model, neutrinos are strictly massless. I cannot have neither Dirac or Majorana masses, and we have to extend the particle content to explain neutrino oscillations. The simplest of these extensions is the addition of right-handed neutrinos. I will need at least two right-handed neutrinos to explain the two mass splittings of the oscillations. So these right-handed neutrinos are also known as heavy neutral lepton and are singlets of the standard model gauge group. So I will have now my Yukawa interaction of the right-handed neutrinos with the left-handed neutrinos that is giving me the Dirac masses after electroweak symmetry breaking. And also I have a new kind of term that is now allowed for the right-handed neutrinos because are singlets. So I can write this Majorana mass term that it incorporates a new physics scale, this Majorana mass, which is not related with his mechanism. It has nothing to do with the electroweak symmetry breaking, and therefore I have a new mass scale in my Lagrangian that I have to determine through the experimental. So I need experimental verification for this Majorana mass scale. So the neutrino mass matrix will be diagonalized by the unitary matrix U. Is not longer the PMNS because now I have a bigger matrix depending on the number of right-handed neutrinos that I have introduced. Nevertheless, this big matrix U is written in different subblocks. The first of this block is the one that is explaining the mixing among the active sector, electron, muon, and tau, and the light sector, nu1, nu2, and nu3. This used to be the PMNS matrix. And the other block that is interesting to us is the one that is connecting the active sector, the electron, muon, and tau, to the heavy sector of the whatever number of neutrinos I have introduced, the nu3, nu4, nu5, nu6, and so on. So the first block used to be the PMNS matrix. Now it is deviated from unitary by this amount, and where the theta is the mixing of the active and the heavy sector, which is in the seesaw limit a combination of the Dirac and the Majorana mass matrices. So in the type 1 seesaw, the smallness of the neutrino masses is coming from the suppression of this heavy Majorana mass scale that appears in the denominator. The price that you have to pay in the type 1 seesaw is that the mixing between the active and the heavy sector is going to be suppressed by the same amount. So it is the same amount of Majorana mass scale in the denominator that is suppressing the light neutrino masses is also suppressing the mixing. We can see this with some numbers. For instance, if we want to explain the Planck limit of masses of the light neutrinos of the 0.1 electron volt, and I impose a Dirac mass of the electroweak scale, this is, let's say, Yukawa's order 1, I end up with Majorana masses of 10 to the 14 GeVs, which is in this game for the theta, it implies a mixing of 10 to the minus 12. So remember that this mixing is what it appears in the charge current interactions, which are weak interactions, meaning that my new weak interactions for the heavy neutrinos will be 10 to the minus 12 weaker than the weak interactions, which is making the type 1 seesaw really challenging when I try to test it in experiments. There is an alternative solution for the type 1 seesaw, which is what is called the low scale seesaws, motivated by other kind of seesaws like the linear or the inverse seesaws, where the smallness of the neutrino mass is not coming only from the suppression of this huge hierarchy of scales, but from an approximate symmetry. In this case, the lepton number symmetry, if I introduce this symmetry to my heavy neutrinos in this way, for instance, if I have 3 heavy neutrinos, 2 of them with opposite lepton number, and the third of them with 0 lepton number, I will end up with these Dirac and Majorana mass matrices, and if I plug them in my Majorana masses for the light neutrinos, with this texture of the lepton number symmetry, I end up with massless neutrinos, which is obvious because the Majorana masses of the light neutrinos are violating lepton number in 2 units. So the lepton number symmetry is protecting it and is making me to end up with massless neutrinos. The interesting point on here is that the mixing, which is made of these Dirac and Majorana masses, will have an arbitrary number now, because anything that I can plug here, a Yukawa or a mass, is not connected anymore with the suppression of the masses of the mass of the light neutrinos because they are massless. So I can have an arbitrary number for my mixing with still massless neutrinos. This is not the scenario that we want because we have introduced the type 1 seesaw to explain neutrino masses, but we have to do perturbations of these scenarios, and I have to introduce a small lepton number violating terms, the epsilons and the mu, to end up with now massive neutrinos, but small numbers that are correct. They are limited by these epsilon and mu terms, so I can have masses of the order of the electron volt, while my mixing will still be large. It is exactly the same expression with corrections up to epsilon and mu terms that are small. So I can have, again, large mixing with the masses of the light neutrinos as small as I want. So this is the kind of scenarios that are more interesting in the community right now. From these low scale seesaws, the most minimal of them is when I introduce only two heavy neutrinos. Okay, I have to introduce them in this way of opposite lepton numbers. So it will be here my heavy neutrino 1 and my heavy neutrino 2 with opposite lepton number, and the epsilon and the mu to be these lepton number breaking terms. So when I solve the neutrino masses, the seesaw equation, to relate my parameters of my model, the Yukawas and the mass matrix, to the measurements on the experiment, these are the PMNS angles, the mass difference, and so on. So I want to relate my Yukawas to the experimental values. I end up with strong correlations in this minimal scenario. In particular, for only two neutrinos, I see that all the flavor structure, my three mixings, will be given in terms of one overall scale theta and the two unknown values, the delta CP phase and one of the Majorana masses. The other Majorana mass is absorbed because we only have two neutrinos. Everything else is given by the experiments. So this is the case for the normal hierarchy. We have similar equations for the inverted hierarchy, but the still is the same. All the phenomenology will be given by three parameters of the flavor structure. If I move into three neutrinos, then I have a similar situation with my third neutrino to have this lepton number 0. So I have the Majorana mass for this guy. The other two will have this pseudo-Dirac form. And what I see is that the correlations that I have in the past for only two neutrinos are relaxed. And in particular, I still have correlations, but they are more relaxed. I only have that one of my three mixings, the one from the taus, for instance, it is given by the other two, and my three parameters, the alphas and the Dirac phase, and the overall mass scale of the neutrino. That will be either the one or the three, depending on the normal of the inverted hierarchy. So all the flavor structure for this three neutrino case is determined up to 8 free parameters here. And that's all. If I introduce more neutrinos, 4 neutrinos, 5 neutrinos into the game, then there are no correlations, and I can explain any pattern of the experiment with whatever combination I want of Yukawas and Majorana masses. Okay, so just a piece of information. Most of the experiments are providing the sensitivity results in what is called the single flavor dominance. This is that they assume that my heavy neutrinos are only mixing with electrons, or only mixing with muons, or only mixing with taus. So it is one mixing at a time, and it is given in this form. So if I construct this object, what is the normalized mixing matrix elements, is only the mixing matrix element over the sum of the three mixing elements. It is a quantity that it will go from 0 to 1. It corresponds to the three axes of an sphere, and inside I will have whatever pattern or allowed pattern of my Yukawas and Majoranas. So the projection of this pattern on the surface of the sphere is what is giving me the ternary plot. Okay, so this ternary plot, the corners correspond to this electron muon or tau dominance. So I have only mixing with electrons here, only mixing with taus, or only mixing with muons. So now if I take my minimal model of only two neutrinos, due to these strong correlations, and that I only have these three parameters, when I scan over the three parameters, allowing the oscillation parameters within the 2 sigma region, I recover these blue or orange regions that are meaning that from all the area of my triangle, at 2 sigma, only this combination of the mixings are allowed by neutrino oscillation experiments. I have different results for normal hierarchy or for inverted hierarchy because the equations are slightly different, but it's a similar situation. So as you can see, the corners of the triangle are disfavored, are not colored, so they are disfavored at 2 sigma by neutrino oscillation experiments. But there are some other regions that will have a different mixing pattern that is still allowed. Everything is allowed beyond 2 sigma, but at 2 sigma, I have other flavor structures that could be interesting in the experiments. For instance, for the normal hierarchy, the structure with muons and tau mixing at the same time, or for inverted hierarchy, the structure of 3 degenerate mixings. If I go beyond the 2 neutrino scenario, for 3 neutrinos, I see that I almost recover the whole area of the triangle, almost. For normal hierarchy, the electron dominance is still excluded at 2 sigmas, and for inverted hierarchy, the 3 corners are not favored at 2 sigma, but more or less. And if I introduce more like-minded neutrinos, then again, this game is lost because all the area of the triangle will be recovered because I don't have these correlations. So from now on, I will say that my flavor neutrinos will have a combination of the massive neutrinos and the unitary matrix elements. I will not say how many neutrinos I have in the game. I will have whatever number I need to explain neutrino masses and to explain the patterns of neutrino oscillations. What I will say is that from all the heavy neutrinos I have in the game, only one of them is light enough to be produced in the experiment, or it has a mixing large enough to be detected in my experiment. Okay, the others will have other masses, other mixings that are not affecting my experiment. So in this simplified view, I can explain all the phenomenology with 3 mixing angles, the U alpha n, electron muon or tau, and 1 mass for this heavy neutral lepton. So the question here is, what is the present status on the mixing of this heavy neutrino? And the answer is that it really depends on the regime of the Majorana mass. So for light masses in the electron volt, these heavy neutral leptons are light enough to be participating in the neutrino oscillations. So my picture of 3 neutrino oscillations that I have in the standard model will be modified because my heavy neutrino will impact this oscillation. I can have oscillation to the 4th state. And this can be searched in many neutrino oscillation experiments. For instance, I have here the new mu disappearance that is expected in minus or minus plus experiment. The probability will depend on neutrino oscillation parameters, for instance, the atmospheric mass splitting or the atmospheric mass angle. If I introduce a 4th neutrino into the game, then my expected probability of new mu disappearance in the experiment will have sensitivity to the new angle, to the 4th state, or sensitivity to the mass difference to the 4th state. And that is how they set a bound on the mixing to the 4th state as a function of the masses to the 4th neutrino. And you can see here that above 10 electron volts, then the oscillations are too fast to be resolved in the detector. This is called the average out regime. And I see that over 10 electron volts for the masses, I will end up with a bound that will be a straight line forever. But I will enter in a regime that I will have some other experiments that are set in a stronger constraint. For instance, the beta decay searches. So in the standard beta decay searches of the standard model, I will look for a nuclei or atomic elements that are decaying into different nuclei or different isotopes, let's say. And I study the energy spectra of these electrons that are emitted. So for massless neutrinos, I expected the spectra to have a continuous form that is finishing in the endpoint, the A0 of this beta decay spectra. So the endpoint is the energy that has from one isotope to the other. If my neutrino is not massless, it is massive, then I expected to get part of this energy for the mass. So that is why the spectra will be modified at the very end of the decay. So that is how experiments like Catherine are looking into the endpoint of the beta decay spectra, and they are looking for this line to be deviated from the standard scenario of massless neutrinos, and that is how they set a bound on the effective masses of the electron neutrino, which is the one that is participating in the beta decay. Now, if I introduce a fourth neutrino or more than neutrinos that are heavy but light enough to be below the endpoint of the beta decay, so the masses of my heavy neutrinos have to be below this exchange of energies between the two isotopes, then I will have a different contribution to the spectra, okay? I will have this blue contribution to the spectra that is coming from the heavy neutrino that will finish the spectra at what is called the kink energy, that is the endpoint minus the mass of my heavy neutrino. So I will have that what I measured in the experiment is a spectra that has a kink at the very same point of the mass of my heavy neutrino. So they do look for different isotopes, looking for the spectra and looking for these kinks in the spectra. They don't see anything, and that is how they could set bounds on the mixing versus the mass. For higher masses, I enter in the peak searches, in which they produce heavy neutrinos via the decay of pseudoscalar mesons. So they look for pseudoscalar mesons because in the standard model, it is a two-body decay with a monochromatic energy spectra. But if I have additional contributions from heavy neutrinos, I will have different peaks in the spectra at different energies with different lines. So I can compute the number of events with heavy neutrinos over the one of light neutrinos. It will be a function of the mixing of these heavy neutrinos and the mass of the heavy neutrino. And that is how, again, they can set a bound on the mixes versus the mass for MEV to GeV. In the same region, we have some competitive results from Dam experiments in which it is something similar. They produce the heavy neutrino in the decay of a meson, but if the mixing of this heavy neutrino is small enough, then this heavy neutrino will fly and it will propagate. And if I'm lucky enough, it will decay inside a detector of my experiment, giving back a signal of standard model particles. So here I have to pay the price of the mixing twice because I produce the neutrino and I decay the neutrino to a standard model. So the number of events will be the mixing to the fourth as a function of the mass. Then I enter in a different region up to the electroweak scale, where these heavy neutrinos are proved in colliders via the W of set interactions. In particular, they can look for display vertexes in which they produce this heavy neutrino, it flies, then it decays back to the standard model, but it produces a decay vertex of different measurements for Atlas, or they can also look for two leptons with the same sign in the final state, which is a characteristic signal of Majorana neutrinos. And finally, above the electroweak scale, my heavy neutral leptons are no longer produced in the experiment, but there is still hope because they will induce deviations in the electroweak and flavor observables that are precise measurements that we have. Because remember that what was happening in the charge current interaction was not the PMNS, if I have heavy neutrinos, is the PMNS deviated from unitary by this amount eta. Eta was a combination of the mixings of my heavy neutrinos. So whatever process that is mediated by charged current interactions, I can do precision measurements and I can induce information on this mixing. For instance, if I look to the G Fermi that is measured in the muon decay, I will say that what is called G Fermi in my Lagrangian is not longer my measurement in the experiment because the matrices that are happening here are not unitary, are not the PMNS, and therefore I have a combination of these eta elements. And when I propagate this G Fermi measured in the muon decay to, for instance, an observable like the mass of the W, I will see that it will have hints of the mixing of these heavy neutrinos. And when I measure kinematic measurements of the experiments of the mass of the W and I compare to the predictions of the mass of the W, then I set constraints on the mixing of these heavy neutrinos. So this is the present status. If I focus on the regime of peak searches, like TRIUMPH, PNU, NA62, beam dams like T2K, BBC, CHARM, colliders, Delphi, Atlas, CMS, or the non-unitarity, that is this purple line here. So this bound will continue here forever and ever because it doesn't not depend on the mass of the heavy neutrinos. They are decoupled. So I mean, they are decoupled, they are integrated out. So whatever bound I get here, it will continue forever. So this is the situation for electron neutrinos. I have a similar situation for, for the mixing with muons. Sorry, this was for the mixing with electrons. This is for the mixing with muons, and this is for the mixing with taus. Okay, there are complementary bounds that are not laboratory bounds, placed in color. This dust line here, it is the bound that comes from cosmology. In particular, this is BBN or CMB modifications. So the heavy neutrinos will modify my cosmology predictions, and therefore these regions here are not allowed in any of the mixings. Okay. In the future, or in the rest of the seminar, I will focus on the colorful bounds that are coming from laboratory searches. Just to tell you a piece of information, this is a GitHub repository where we are collecting all the present bounds on the different experiments. So it is just a repository that you can clone on your computer, and you can get all these lines and the future lines of future experiments, and you can do this kind of plots from some scripts that we have in the GitHub. Sorry. So the question here is, what will be the near future situation coming from beam dam experiments on the mixing of my heavy neutrinos? And for that, I will use the Dune experiment as an example of how to do this for future detectors. So probably you all know what is Dune, but just in case I will do a brief introduction. It will be the new generation of neutrino oscillation experiments. It is placed at Fermilab in the USA. They use high energies, or they produce a high energy beam coming from the collision of 220 GeV protons on a beryllium target with a quite large luminosity. So this target will produce kaons, pions, and other heavier mesons like D, DS, or Bs. These mesons are propagating in the decay pipe, and at the end of the decay pipe, it is an absorber to get rid of the whatever is left of the mesons there. And as a result, I will have a pure neutrino beam that it is pointing inside the Earth to be able to reach an experiment that is, the far detector that is farther away. I will explain that later. So what is important in this seminar is that the near detector, it is actually a combination of three detectors. We have the NDLAR is a liquid argon detector, which is quite a big volume. You can see here a person, so it is 7 meters, 3 meters, 5 meters. Then it is followed, or it will be followed by the NDGAR, which is a high pressure TPC gas with an electromagnetic calorimeter and a magnetic field to separate the charge. And it is an on-axis beam for monitoring the fluxes. So the two liquid and gas detectors can be moved out of the neutrino beam to measure off-axis oscillations. So this is called the Dune prism. So my neutrino flux will keep going inside the Earth, and it will reach my far detector that it is 1,500 kilometers away in South Dakota mines. So this is the end, 1,300 kilometers away. So this is the whole experiment of Dune. I will be focused only on the near detector part. So there will be there were some previous results on the sensitivity of Dune to heavy neutral leptons. All of them were based on this approximation where they were using the fluxes on light neutrinos, and they were just rescaling them with kinematic factors to compute the fluxes of heavy neutrinos. So this is an approximation which is working well because it is giving you the correct rate in the sense that you are correcting to the decay width of whatever meson into the heavy neutrino, which is giving you the correct number of heavy neutrinos if you want. However, this factor does not depend on the energy. It does depend only on the mass and on the mixing. And therefore, we are expecting deviations on the energy and therefore on the angular distributions of the heavy neutrinos that are not implemented in this approximation. And why is this important? Because of the acceptance of the detector. So the acceptance of the detector is computed as the angle that my beam is formed with my detector, right? So this angle of my neutrino flux is set in the laboratory frame. So remember that this is a target, so all my mesons are highly boosted in this experiment, and therefore my neutrino is highly boosted, but it's making that when I go from the zero mass to the massive case, my angle to be shrink. So this is enhancing the acceptance of the detector because of the boost factor. So the heavier is the heavy neutrino, the larger is the boost, and therefore the better will be the acceptance of my detector. Meaning that this approximation that was not depending on the energy could not have the right information of the heavy neutrinos inside the acceptance, because they would have only the acceptance of the light neutrinos all the time. On top of this, we also found some, let's say, ambiguities or differences in the decay width, in the analytic decay width. And that is why we needed to do a full review on how these mesons are interacting with the heavy neutrinos. So let me go a little bit quick on this part because it is not that important for the conclusions. So this is the leptonic part of the Lagrangian that contains the W and the Z interactions of my heavy neutrino. Also, the quarks are connected to the W and the Z via the W and Z currents. I can split them into the vector and axial currents because it will be more easy for the computation. And on top of this, I have to define what is called the decay constants for the pseudoscalar or the vector mesons. So this is just a sandwich between my whatever meson, the pseudoscalar meson, and nothing because it will decay with the axial current given by the decay constants f pi in this case. And very similar for the vector mesons with the polarization vector. So inside these decay constants, I have the axial and the vector currents, and I also have the 8 Gell-Mann matrices that have linear combinations of these Gell-Mann matrices. So I will start from the pseudoscalar mesons. These are the pi 0, the eta, and the eta prime. And I have to write the quark content of these pseudoscalar mesons as linear combinations of the Gell-Mann matrices. In particular, it will be the diagonal ones, the lambda 0, lambda 3, and lambda 8. The first of these combination is giving me the pi 0, which is just the lambda 3. And then the eta and the eta prime are different combinations of the lambda 0 and the lambda 8. Okay, so I can write my axial current of the Z bosons as linear combinations of these 3 axial currents, in particular this one. So I will keep going, focusing on the pi 0 because it is without any other factor. It's a linear combination of the Z and the third one. So at low energies, I can integrate out my Z boson, and I will have a pi 0 connected to 2 neutrinos. I can write down the amplitude of this process as this equation, where this is the decay constant of my pi zero. I introduce here what was my current, so I will have the momenta, and moving into configuration space and moving this momenta into a derivative, I can write down what will be my operator that is leading into this amplitude. And now applying the Dirac equation and assuming that my final particles, the pi zeros and the neutrinos are on cell, I will have my effective operator that is describing how my pi zero is interacting with two neutrinos. So you can see here that if my two neutrinos are massless, these m's are going to zero, and then I will not have a decay of a pi zero into light neutrinos as it is happening in the standard model. While when I have the masses, then I have what is called the chiral enhancement, and I will see that this decay, it will be dominated by the decay to two heavy states. I can follow the very same game and compute the effective operators of the eta 0 and of the eta 8. And then it is a rotation to the interaction mesons, the eta and the eta prime, which are in the mass basis, given by this rotation. So I can build my operators in the mass basis for the eta and the eta prime. So this was for the neutral pseudoscalars. I can do the same thing for the charged pseudoscalars. These are the pi or the kaon. I start building the axial currents as combinations of my Gell-Mann matrices, and I build up my charge current axial contribution of the charge current. Here we have the elements of the CKM matrix because of the different quarks that I have. So I do exactly the same. I integrate out my W and I write down my amplitude describing a decay of a pi zero into a lepton and a neutrino. And then I apply the Dirac equation and I end up with these operators. So I repeat this for the other mesons, the kaons or the B mesons, and for the vector mesons, which is again for the neutral or the charged. And I write down the set of operators that are describing interactions or decaying into leptons. Then I will have also decaying of mesons, in particular pseudoscalar meson, into a lighter meson, and a neutrino and a lepton. For instance, this can be kaon decaying into pion, neutrino, and a lepton. So this the amplitude is a little more complicated because the decay constants are written in terms of two form factors, the F plus and the F minus. This has been tabulated by lattice people. So we can use this information with given parameterizations to write down my operator on how different pseudoscalar mesons are decaying into lighter mesons, a neutrino, and a lepton. So we collected all of these effective operators in fine rules model files that we made publicly available. So you can download these model files and you can implement these model files in generators like MathGraph. So Monte Carlo generators that will produce the decay of mesons into heavy neutrinos, two-body or the three-body, and also the decays of heavy neutrinos into light neutrinos or mesons and neutrinos. So with these MathGraph simulations, I will compute my fluxes of neutrinos that are pointing the near detector without the approximation of these light neutrinos that were used in the literature. So this is an example of what we got. In light, we have the histograms of the mesons decaying into light neutrinos. So this will be the histograms that you will get from the light neutrino approximations, the light ones. And in darker blue, you have the contributions when you have the correct energy distribution of heavy neutrinos. So this is, for instance, kaon into heavy neutrino and an electron, assuming a mass of 200 MeV, or in the case of the Ds. So as you can see, the acceptance is quite different, and that will be giving different results. This effect is more relevant when you go closer to the kinematic threshold of production, so closer to the mass of the pion or the mass of the kaon or the mass of the disk. For heavy neutrinos of this mass is when this effect of the acceptance of the detector is larger. So in order to compute the sensitivity, I have to go event by event and compute the probability of my neutrino to decay inside the path of that is crossing inside my detector. This probability will be convoluted by my flux of heavy neutrinos. And when I multiply by the branching ratio of my heavy neutrino to decay in whatever channel, let's say heavy neutrino into 2 electrons and a light neutrino, I will be computing the expected number of events of this heavy neutrino decaying into the pair of electrons and a neutrino. Okay, so when this number of events is below than 2.44 is where I can set my 90% confidence level that I will not observe any of these events, and that is where I can set my current limit at 90%. Okay, so this is the results that we got for the Dune near detector of the mixing with electrons as a function of the mass of the heavy neutrino for different decay channels. For instance, electron and neutrino, muon neutrino, and so on. This is the result for muons and the result for taus. I can combine all of these decay channels, and I will get the answer to my question, which was what will be the future sensitivity of experiments like Dune to prove for heavy neutrinos on this regime of order 1 GeV neutrinos. So now I move into a different sector, which is what will happen if these neutrinos are described in effective theories. So imagine that I am sitting here in my low energy world, and I think that it will be a different physics that is happening at higher energies above a cutoff lambda. So above this cutoff, I will have new physics that will could be new particles, new interactions, or something. And my question is, what will be the effect on my world, on the low energy observables, of these new particles that could be existing at a higher energy? So this is parameterized by the standard model effective field theory in a set of operators. So they consist in towers of higher dimensional operators. The dimension 4 is the standard model, which is what we know. The dimension 5 is only one operator, is the Weinberg operator. Dimension 6 will contain a set of dimension 6 operators, and so on. So at the given dimension n, I will have a tower of these operators that they will encode the effects of the new physics. These operators are non-renormalizable, and they are built from pieces of standard model things, or standard model particles that I already know. So they have to respect the fundamental symmetries of the standard model. These effective operators are suppressed by inverse powers of this cutoff of my lambda, that was the cutoff of my energy where my physics is new physics living. And the strength of this operator is controlled by what it is called the Wilson coefficients. So the higher is the dimension where I go, dimension 6 or dimension 7, and so on, the greater will be the number of operators I have, because I can build with more pieces of a standard model. So this is escalating quite fast. However, I am expecting that the effects on my low energy observables will be smaller because the suppression of this operator is higher. Okay, so the suppression is larger for higher dimensions. So when I have effective field theories and heavy neutrinos, how to combine both things, I have two options. If my heavy neutrinos are living above this cutoff, then the heavy neutrinos will be part of the effective field theory. Okay, so I will have dimension 5 will be the Weinberg operators giving me Majorana masses for the light neutrinos from the suppression of these heavy neutral leptons. Dimension 6 will give me the non-unitarity of the PMNS matrix, meaning the mixing of these heavy neutrinos. So if it is above the lambda, I will not care. But if it is below the lambda, the heavy neutral lepton, then I will have to introduce the heavy neutral lepton as fundamental building blocks of my theory when I am gluing these operators. So I will have new operators in the standard model field theory because I have a new ingredient, the heavy neutral lepton, and this is called as a nu-SMEFT because it contains the heavy neutral leptons. So at dimension 5, there are only two new operators. The first one is the dipole moment, which is this operator, after electroweak symmetry breaking. This operator is giving dipole moments between the two neutrinos. I will be working on this seminar on the assumption of only one heavy neutral lepton, meaning that this operator has to vanish because this is antisymmetric matrix. The other dimension 5 operator is the Higgs mass, which after electroweak symmetry breaking, it will generate a contribution for the Majorana masses. And more interestingly, it will also contribute to heavy neutrino decay, for Higgs decay into heavy neutrino. So I will have an H and two neutrinos, and I can use the Higgs signal strength. This is a relation of initial particles into Higgs or Higgs into final particles. So when I look for new physics, I can do the ratio of whatever is my new physics over the expected physics of the standard model. This is 1 if there is nothing new, and this is how it is defined, this mu f, for instance. So I will focus on the mu signal strength of final particles of Higgs decaying into something new. So Atlas and CMS are measuring precise values of the Higgs into gamma and Higgs into 2Ws, and they are measuring a combined bound of signal strength that is 0.94. So if it is 1, then it will be a standard model. Like if it is different from 1, then it is new physics. So I can use the bound on the signal strength to set a bound on the Higgs to two neutrinos from this coefficient, from this ratio of the branching ratios. So I will get a bound on the coefficient of the dimension 5 operator. So in particular, I will have a bound on this coefficient to be below 3 10 to the minus 5 for masses of the heavy neutrino below 40 GeV. So when I have masses over 40 GeV, then the phase space is reducing the branching ratio, and then I will start losing this bound. So consider that this bound is independent on the mixing of the heavy neutrino. So this is a quite powerful tool to set constraints on this dimension 5 operator because it is independent on the mixing of the heavy neutrino, only on the mass. So at dimension 6, I have a full set of observables. This is quite large. I will have a Higgs mixing, tensor currents that are giving me dipoles, a bosonic current that could be neutral or charged, or for fermion interactions that there are a lot of them, and I am just pointing here 2 examples of neutral or charged for fermion interactions. So in the next 5 minutes, I will assume that only one heavy neutrino is negligible. So we have one kind of mixing, and I will study the bounds on the coefficients of these dimension 6 operators, assuming one operator at a time. Okay, this is the status right now, that only one of these operators is happening, and then how it will be the bounds on the coefficients. So I will start from the Higgs mixing. After electroweak symmetry breaking, I have contribution to the mixing. So I will have, this is just a standard Yukawa interaction dressed with 2 additional mixings. So I will have a mapping between what was called my unitary mixing, the element of my mixing matrix, and the coefficient of this operator dressed with other combinations of my BEF and my Majorana mass. So it is just a mapping between my standard mixing of the type 1 seesaw and my coefficient of the dimension 6 operator of the hysterex mixing. I also have contributions to the mass of the light neutrinos. However, in order to explain mass neutrinos, we have to implement more than one heavy neutrino. So in principle, it could be cancellations among the different contributions to these operators. So we will not consider this part. And I will also have invisible Higgs decay into a heavy neutrino and a light neutrino. And again, I can use the signal strength to set a bound on this coefficient at 95%. Well, using this bound, I can set a 95% confidence level constraint on this coefficient. So this is the result of the coefficient that is mixing with electrons of the hysterex mixing as a function of the mass. So it is the combination of colorful bounds that I have before, because it is a mapping between the mixing of the heavy neutrino and an electron, just converted into this effective operator. And I also have this bound of the Higgs into electron neutrino and a heavy neutrino. I have similar bounds for the coefficient assuming mixing with muons and coefficient assuming mixing with taus. In the context of the bosonic currents, in the neutral ones, after electroweak symmetry breaking, I will have an effective coupling of the set into two heavy neutrinos given by this coefficient, the CHN. So these neutral currents could mediate decay of either pseudoscalar or vector neutral mesons. These two things are suppressed in the standard model, the pseudoscalar because of the chirality flip that you need to explain it, and in the vector mesons because they are basically hadronic or electromagnetic. So in the standard model, these two decays are quite suppressed. But if I have a heavy neutrino, then I will have different contributions, and in principle, I can use results from experiments like NA62 or Babar that they are looking into the case of pi 0 or upsilon into heavy neutrinos. So I will use these two experiments to set constraints on the Wilson coefficient of the CNH. I can also use the monophoton searches at colliders. This is, for instance, at LEP. It was looking for electrons into gamma-gamma photon. So it will be, in this case, electrons into nothing because it's my my heavy neutrinos and a photon. So we could use this result from this paper where they were using the monophoton searches to set constraint on vector coupling of some dark matter, phi, to recast these bounds as the couplings on the coefficient of this dimension 6 operator. Another bound that we can use is the supernova cooling. Light neutrinos are the dominant cooling mechanism to cool down the core collapse in supernova, because they do not interact with matter that much, so they can absorb the energy and take it out of the supernova, basically. So in this case, I will have different bounds. For instance, if the heavy neutrino has a large mixing, it will be trapped inside the supernova, and it will keep the energy. So I will have a lower limit. And on the other side, on the other hand, if the mixing is small, then it will extract energy faster than the light neutrinos from the supernova, and I will have again an upper limit. This upper limit, it is also competing with the fact that we'll have generation of gamma-gamma into pi zeros, and my pi zeros from the first of these ballet points, it will produce two neutrinos. So I can again use the NA62 results to set constraints on the production of these heavy neutrinos via pi zero. So, well, the last of them is the decay of the set into two into invisible. So I can use the set invisible measurement from LEP to set constraints on this operator. So this is the present status of the LEP into two neutrinos, LEP monophoton searches in pink, the BABAR and the NA62 searches of pi 0 or epsilon into heavy neutrinos, or the supernova bounds. And finally, I will go faster because I am finishing my time. For bosonic currents, after electroweak breaking, I have similar things. So I have an effective coupling of my W with a heavy neutrino. So I have what is an effective mixing with this operator. So I can rescale the bounds from almost all the experiments I have. For instance, if you remember, the PIC searches is a production of a heavy neutrino in the decay of a meson. So I can reuse my decay of a meson as a decay, that is mediated with a mixing of the type 1 seesaw as a mixing of my effective operator. I can do the same for Bindam experiments. The problem of the Bindam experiments is that sometimes in the decay of my heavy neutrino, they implement charge current and neutral currents because the neutrino could be mediated any of them. And this bosonic currents is only explaining the charge contribution. So I have to rescale my number of events, removing the part that was explaining neutral currents in the standard model. So it is basically the same, but removing the neutral current component, and it goes with the mixing to the fourth. You remember in the beam dams, you have the production and the decay. For the bounce from colliders, it is practically the same. If it is coming from the set boson, then it does not apply because it is neutral current. If it is coming from a W, it is the same procedure as beam dam, and I have to look to the final state of decaying of the heavy neutrino, and if it is neutral current mediated, I have to remove it from the number of events. And finally, I have also the decay of a charged lepton into a lighter charged lepton and a heavy neutrino. So I collect all the PIC searches, beam dams, colliders, and decays of leptons, and these are my bounds for the muon sector. I have similar bounds for the electron and tau sector in the backup slides. Again, these kind of plots are in this GitHub. So if you are working with models that are counting with these effective operators, you can just download the data and the scripts, and you can do whatever you want with the model. So I will go to my summary. Neutrinos, from my point of view, are one of the most promising open windows for the new physics. Depending on the mass range of these heavy neutral leptons, I have very different bounds to the mixing. However, no matter what is the bound from from masses of the electron volt to whatever mass above the electroweak scale, the bounds are constrained to be always below 10 to the minus 2 or lower. We have computed expected sensitivity of new generations of beam dam experiments or neutrino experiments such as Dune. For that, we have implemented a new fine rules model file that we made it public. And we have seen that Dune could test a large part of the parameter space in the future. And also we have seen that the effective operators are very useful when you are describing new physics involving heavy neutral leptons. And we also have seen that present laboratory searches, not colliders or not any other searches, but present laboratory searches are constraining the dimension 6 Wilson coefficients of the nu-SMEFT. And with this, I finish my talk.
Okay, thank you very much. It was a very, very nice talk, very comprehensive. Okay, so let us start with the questions. So there's usually a lag between the transmission and the viewers. So let's start with the people in the audience. I for sure have a couple of questions, but let's see if Alejandro or Roberto have any questions. If not, I'll go. Oh, go ahead.
I have a question regarding because most of the constraints that you presented are based on, let's say, collider and other type of the studies that in laboratory. But is it any chance to have a implication for the case of cosmology in the, let's say, early universe? I know that you use the constraint of the sum of the masses for the light neutrino, but this with the operator, like to restrict like kind of the processes
Yeah.
happening early, like I don't know, leptogenesis or something like that. That
There are some works on dimension 5 on this heavy neutrino into the Higgs into heavy neutrino. There are things as well, some on the dimension 6 operator, not a lot for leptogenesis. But it's not as trivial to do this kind of recast as we were doing, because the present bounds on cosmology are based on standard cosmology. If you introduce heavy neutrinos, then the picture is changing. Depending on how you change that picture, then the bounds itself are changing. So doing the recast into a different bound is not as trivial as what we have done here. It was only the bounds on the type 1 seesaw are like this by itself, because it's what you can see in an experiment. And then it is just translating to a different coupling, if you want, that will be from a different operator. So what you are proposing will be more convoluted, will be more complicated. Of course, I think it will be done in the future, where when maybe with the help of computers, because there will be correlations. Also, this work is quite simple in the way that we have only implemented one operator at a time. If you open to have different operators at a time, then you can have funny things like production and decay from different operators. And that will play a role in cosmology as well, because the production and the decay will have different impacts in the early universe. So I think there are some works, but not many, and I think they are complicated from my point of view.
okay, thank you.
You're welcome.
Super. What about bounds from neutrinoless double beta decay? And because you assume that you have only one heavy neutrino accessible to experiment and very large mixings, right? So in those situations, usually you had bounds from neutrinoless and from corrections to loop corrections to the masses of the light neutrinos. So I was wondering if you had a look at those.
Loop corrections to the masses of the light neutrinos.
Light neutrinos. These are usually more important for heavier neutrino masses, right? Like 100 GeV or so. And for lighter masses, usually you had some important bounds from a neutrino-less double beta decay.
Yeah, I mean, I would say that neutrinoless is playing an important role at very low masses, but in this here in this regime, no. So it will be below, let's say, GeV or EV. For MEV neutrinos, there is no impact of neutrinoless, as far as I can guess.
On the standard seesaw, there is.
On the what?
On the standard seesaw, not with effective operators, but on the standard one, there is around the GeV scale or so, if your mixing is large enough.
Okay, I will look at it, but I thought it was for lower masses neutrinos. So one. But this loop effect, you mean?
No, the loop effect is on the masses. But for neutrinoless, it's just the same, but you have a heavy neutrino on the diagram, right? And that usually gives you a contribution to neutrinoless, which can be of the same order of magnitude of the contribution of the light neutrinos.
Right, but my question is how to translate this into this kind of coupling. So what is the difference with an effective operator?
Yeah, I mean, you can, well, in an effective one, I don't know. That was my next question. But okay.
That's why I was thinking, like, I didn't see the connection of neutrino-less here.
No, here I don't know. That was the next part because on your first bounce, I noticed that you didn't put any bound on neutrino-less double beta decay. And then the next question was gonna be if neutrino-less can put bounds on these ones also. I guess it depends if you have lepton number violating operators there or
So in particular for the dione bounds I saw, this is not playing any role because those are Dirac neutrinos. So there is no contribution to neutrino-less because of the Dirac nature of the neutrinos. Here in the Majorana and you have lepton number violating things, it could be some. I don't know how competitive they are. I will give it a thing.
Okay, let me ask you also regarding the limits on the constraints coming from the PMNS unitarity that were in the I noticed that there was a line that kind of like stopped at some point. Maybe you can go back to it's a long way back.
Yeah, maybe I can even zoom. So you mean
yeah, I think it's that one. Yeah. Right. So where does it stop the bound on the PMNS? If you keep on going left, at some point you do not have that bound.
yes, because
that's
below
surprising.
I mean, this is coming from ion decay. The G
Oh, I see.
So below that, there would not be.
Okay,
basically,
so the bound is from G mu. Okay, I get it.
so this is G Fermi from the muon
Yeah.
decay. Then is the ratios of universality, CKM universality. Then if you go above the electroweak scale, then you have other observables. That is why it is a small gap here. I mean, jump.
I see.
So yeah, below the mass of the muon, you don't have.
So yeah, okay. So I guess that maybe in a very very optimistic future where you get to test the unitarity from the elements of the PMNS itself from neutrino oscillation experiments, maybe you could get bounds on lower scales. Would you think that would be possible?
No, I mean, from present and near future experiments, there is no way.
No, near future, no, of course not. No.
In the future, with better detectors and the neutrino sector, it could be a way of measuring, yes. But to be honest, before measuring neutrino oscillations, I will have, I will put my hope on a lepton collider that is measuring with higher precision these electroweak and flavor observables. And so with more precision there, then you could see some deviations, like for instance, this mass of the W thing that happened 2 years ago. Well, right now, the mass of the W is not fitting well the non-unitarity, but it could happen with other observables that it is going in the direction of explaining non-unitarity, for instance. So that could be, and I think it would be easier for the. I mean, I think lepton collider will happen faster than a neutrino
than what I'm
experiment
proposing. Yes.
with precision enough to see effect on 10 to the -3, let's say.
Okay, super. We have a question from the audience. We have Gabriel Zapata asking if the bounds, or if all your bounds on the nu-SMEFT are considering the heavy neutrinos as Dirac or Majorana.
These ones are as Majorana. We have in the repository, I think it's already published, the Dirac part, but these ones are for Majorana.
All of the ones in the
all of the one of the SMEFT are assuming a Dirac Majorana neutrino. Sorry, Majorana neutrino, single Majorana neutrino, no Dirac Majorana. But we were doing the same for the Dirac case. I don't know if it is still published or not. There is not many difference. There are factors 2 in some decays, so there are so many differences.
So then going back, in principle, they could contribute to neutrinoless double beta decay. Okay, great.
Yeah, I don't know if it is competitive or not. I had to think about that.
Okay, let's see if Gabriel has got a follow-back question. I don't know if Roberto, you have any other questions. We're running out of time, but maybe there's a time for it. Anything else? No. So okay. Let me ask my final question regarding this study you did in June regarding how the acceptance increases in the near detector when you have the heavy neutrinos. I found that very interesting, right? So in principle, the point there is that you have your meson, and if it decays into heavier particle, they will be more collimated than if they were decaying into lighter ones. And then you're assuming that the heavy neutrino will decay within the detector.
Yes.
Right. So when you say within the detector, are you also considering regions slightly before the detector? Because in principle, if it decays into a muon, you would assume that the muon could
yeah, but the muon could come from cosmics, could come from a halo of other mesons around the detector. So in principle, no, it is. I mean, they look for a vertex that happens inside the volume of the detector. Actually, they remove half of a meter from each part of so the fiducial volume is smaller to be sure that the vertex is happening inside the detector and nothing else was happening there, and suddenly you have a signature to standard model neutrinos.
I see.
So they remove a layer around the detector.
I see.
But we are still doing the official analysis. This is just a fino. So in the physics, we are implementing backgrounds and cuts with energies and so on. So this will be more better done in a future publication.
Okay, super. Yeah, I was thinking that in principle, the heavy neutrinos could also decay into light neutrinos and change your light neutrino flux, but I guess that the effect there will be too small for this. No. Okay, so Gabriel is saying thanks.
I mean, that is looking for a sterile oscillation on the detector.
Sorry, what was that?
But it's looking for a sterile oscillation in the detector, what we are saying.
Yeah, okay, but that would be an effect of an interaction in the far detector. Now, my question was just that you would have the heavy neutrino and it would decay into the light ones and then change the flux. But their effect there is, I guess, you have the smallness of the produced neutrinos and then the lower branching ratios into final states with light neutrinos.
Yeah, I think it's easier to look for the vertex that is happening inside the detector from nothing than measuring an additional neutrino that will happen from the heavy neutrino that is changing your flux. Because the flux is not really well controlled. Actually, the role of the near detector is to measure the flux to do the ratio to the far detector. So if they are decaying and they are doing an extra contribution of the light neutrinos, I don't think it's that easy to while if you see suddenly 2 electrons coming from nowhere in the near detector, then
right. No, of course. Okay, super. So we need to stop already because we've gone way past the time. And
sorry.
No, it's been great. It's been great. So before we finish, please everybody stay tuned. in a couple of weeks, we have Katarina Cosme giving a webinar on something regarding dark matter. So thanks once more, Josu. It's been a great webinar, and we'll be seeing you around.
Thank you so much.
Thank you.
Bye.